YouTube stream also, so I just turned on the sound for that too. Very good. Right, but so my understanding is that there's a wide audience here today, and some of you are from mathematics, but some of you are not from mathematics. This talk is going to be accessible to everybody, because what we're talking about is a totally new way to control pandemics, which is extremely exciting. And by the end of this talk, the hope is that everyone understands the concept, but also sees that the concept is actually quite obvious in retrospect. All right, so let's first talk about pandemics. Unfortunately, pandemics are a problem. The current one is bad, but actually what I care the most about are ways to protect ourselves against even more deadly pandemics. And we can learn a lot from the current one to think about how to protect against future ones. What I will discuss today is a new approach that will help with these extremely dangerous ones in the future and can also help today. First, let's talk about how you control a pandemic anyway, in the old-fashioned way. Or rather, when I say old-fashioned, I mean what we're doing today. One thing, when I give these talks, I will actually just change my background, and then I will draw on that background. So in order to see me most clearly, it is best if you pin my video to be the center of the screen, or if you use a viewing method on this Google Meet in which it makes the speaker the biggest one. For example, when I'm looking at my interface, I see that I can press pin video on my interface, which will make my video the biggest, but I think that's only for my own interface. I'm not sure if there is some hosting method. I don't know if there's a host for this meeting who has the power to put mine on for the whole thing, but I just tell all of you, if you want to make it big, you just go and grab my video, press the pin video, and then it'll become the big screen. All right, so let's talk about how you control pandemics. Well, what are the methods? I actually can see the chat that's here on the Google Meet. So if people want to type as we're talking, that makes this much more interactive. What are the methods? Anyone want to share some thoughts? What are methods to control pandemics? I like to talk more interactively, by the way. It's not much fun for me just to talk. Quarantine. Quarantine is one of the core methods. Actually, quarantine, social distancing, all of these approaches are the fundamental approaches that you use to control diseases. We also have other things like vaccines. We have things like medicines. Those are great. But actually, we need to think about using all methods. Actually, as we can already see, based on what's happening in Israel, where they were ahead of everybody in vaccinations, we've seen that vaccinations are useful. But we have also seen that vaccinations alone don't solve the problem. And so it's important to have many different approaches all working at the same time. But I want to focus on this quarantine and social distancing because those are the bread and butter methods that you use to control disease. So what do? Actually, I'm focusing on this quarantine part. The social distancing is what you do after you have some concept of what you should be careful about. But suppose you have a sick person here. So here's a sick person. Who do you quarantine? I'm just trying to talk about the basic approaches to control disease. You possibly use these methods where you are right now in the university. The family and the sick person. You basically want to quarantine the people who were around the sick person. So you have the sick person and you have the people who were around the sick person. If you ever invite a math professor to give a talk, you end up getting a chalkboard talk like this, or digital chalkboard. And then what you do is you go and quarantine them, meaning that you remove them from the society. That's the basic principle for how we control disease, and it has been this way for hundreds of years. Oh, somebody says they cannot see the presentation. This is now an important detail. May I ask in the chat, can people see the presentation? The presentation is me. It's actually my entire video screen. The way you want to see the presentation is you should not be waiting for Google Meet to pop up a presentation for you. Because the way I like to give my presentation is that I like to be part of the presentation. I'm inside it. So what you want to do is you want to make it so that you can see my video. And then you click on the pin, like the thumbtack, to make my video the big video. If you haven't used this system before, you can use the 3 vertical dots button on the Google Meet controls. It's at the bottom. There are 3 vertical dots that is giving you more options. You click on that. You go up to change layout and you choose in the change layout. Either you can do auto or I believe spotlight, makes it so that it is the person who is speaking. But if you happen to be in a different view, that's why you're not seeing the presentation. Effectively, if you can see the picture of me, you can see the presentation. Okay, good. So let's continue. So the bottom line is that we're trying to control these people. There's the sick person, the people that have been around. And if you think about it from the point of view of game theory, which is very important for human behavior, what you're doing is you're trying to remove these people, but you're removing them against their will. Actually, I'm focusing on the game theory because this is not just a math talk. This is not just a science talk. This is actually a talk about systems. And if you think about one of the reasons why it has been so hard to control the pandemic, it is actually not because of lack of science. It's actually related to human behavior. And unfortunately, if you look at it very carefully, it's because we are asking people to do things that don't directly help themselves, but in fact, they even inconvenience themselves to go and help other people. And unfortunately, when you think about the way societies work and the way people interact with other people, they are most likely to do things that will help them directly. And they may still be nice people, but they are less likely to inconvenience themselves to help others. Actually, I can tell all kinds of stories about this particular instance because I actually myself was one of the sick people. Some people know that I actually got a breakthrough infection of COVID in August. So I am vaccinated, but I unfortunately got COVID. COVID is able to infect people who got vaccinated. It's still good that I got vaccinated because my case was very mild. Actually, it was so mild that it didn't have the standard symptoms of COVID. All I had was a little cough, and I didn't even have any problem with smelling or tasting. Everything was fine. It seemed like just a small cold. But because I was, at that time, in the summer, I was traveling around giving talks. Outside, actually. I was giving talks in parks. Because I was doing this, I went and got tested. In California, which is where I was, in order to get tested, I had to pay for the test. I had to go somewhere, pay for the test. I wanted a fast test, so I had to go and pay for the test. I had to give myself the test, find the results, and when I found out it was positive, I had to voluntarily tell other people and then quarantine myself for 10 days. It was very inconvenient. And actually, as I was doing all of this, I was thinking to myself, there are probably 10 times as many people in the same situation who didn't bother to pay for the test, find out they're positive, and then voluntarily tell everybody. Actually, it runs against human incentives because the only thing that can happen from you paying the money to get the test is that you get inconvenienced. And I'm saying all of this because it's very important to understand incentives. Oh, I can tell you another story. I was just talking to somebody from another university, a student from another university in somewhere else in the United States yesterday. And I was talking to them because they were in a place where there were many, many COVID cases every day. And I was asking, do you guys have mandatory testing? Do you test all of the students, no matter whether they have symptoms or not, every week? And the answer was no. And then I just asked, I'm curious, what do you think is happening behaviorally in your university? Do you think the people who have symptoms are actually going forward to get tested? Because if they do get caught positive by the university with the test, they get quarantined. And the person agreed that actually it might be that there are people who, even though they have symptoms, are choosing not to get tested because they don't want to know. Because the only thing that could possibly happen if you're already infected is that you get inconvenienced. I'm basically outlining all of these human behavioral drivers that are causing it to be very hard to control this pandemic. And I can say, because I witnessed it myself, when I was supposed to not go around in public, it's hard. How do you go and get a banana? You cannot even just go to the store to get a banana. You have to go find some complicated way for them to deliver it to you. And then the minimum delivery order is $35. And I was thinking to myself, it's probably that there are people who have a hard time actually following these orders. Okay. Well, unfortunately, what we have learned from COVID is because it is difficult for people to do things which are against their will, against their own incentives, unfortunately, if the disease was more fatal, if it was Ebola, if it killed half the people who got it, this entire part of the world would be in a huge problem. because we would have lots of people infected and half of them would be dead. So that's why I'm working with a team of other researchers on a totally different approach to fight pandemics. Actually, the significance of this goes beyond protecting University of Puerto Rico. The significance of what I'm talking about could potentially protect huge areas of the entire world. And it's a different way to approach this entire problem. You see, when I approach this problem, I come from the point of view of the area of mathematics which I work on, which is called network theory. And actually, all these people are part of a bigger network. So I'm just going to draw out a network. And this is sort of like an indication of people who spend time around other people. Actually, I should be more specific because I am a mathematician. The way that each of these lines is, each one of these lines represents that those two people spend lots of time physically nearby and often. By the way, this is different from contact tracing. You may have heard of contact tracing. Contact tracing is what we talked about earlier with this diagram. But the principle of contact tracing is you find the person after you know they're sick, and then you go and check who else was around that person within a distance of 6 feet for at least 15 minutes during the periods of time that they were sick. And even just one such interaction, it's important because you need to chase down where the virus went. Our approach is very different. Our approach is we want to build this network where the connections in the network are not just that there was one interaction for 15 minutes within 6 feet, but actually that there are many. Our notion here is that two people are connected in this network if they are interacting the same way as people who live in the same house, or people who work in the same office near each other, or people who go to class and sit next to each other frequently, or people who eat lunch together a couple of times a week. These are our notion of a connection in this network. Ours is actually a more strict network. These are stronger connections. And the reason this is useful is like this. Suppose this is you. I just mark this person as you. The key concept that we actually use from network theory is a definition called the network theoretic distance. But I claim that this distance concept is not new. In fact, you're probably familiar with it already. The network theoretic distance is the smallest number of steps you need to take to go between two people in the network. So for example, what is the network theoretic distance between you and the sick person in this picture? One step means one of these edges. Just to make sure people are still following, can somebody type in the chat? I want to make sure I'm not just talking to nobody. Ah, yes, 3, 3, 3. Right, so it's 1, 2, 3. 3 steps away is the sick person. So the network theoretic distance in this network is 3. I claim that many people are familiar with the network theoretic distance. For example, if you use LinkedIn, LinkedIn is a different network. Their network is one which has people connected if they just know each other. Our network, you have to spend time around each other physically. But on LinkedIn, LinkedIn already tells you there are things like a first-degree connection, meaning that you know that person, or in our system, that you are around them often. And then there's a notion of a second-degree connection. In fact, there's also a common way of calling this degrees of separation. There's another common notion, like 6 degrees of separation is the principle that between you and the president of Uganda, there is a way to go between you and the president of Uganda where you know somebody who knows somebody else, who knows a third person, who knows a fourth person, who knows a fifth person, who knows the president of Uganda. That's the concept of 6 degrees of separation. In our system, people are farther apart than just 6 degrees because you need to spend a lot of time physically around them. In fact, my distance to the president of Uganda is probably in the hundreds. It probably takes a while to get there. Okay, but now this is the notion we have. And the very simple change we made that ends up being quite impactful in how you control disease, theoretically, is that we tell everybody their network theoretic distance to each new infection. Let me be more clear. In many parts of the United States and the world, also I've seen maps of where you are in Puerto Rico, it's possible to see how many new infections there were in the last 24 hours by region. So there will be, your area will have lots of regions, and you can find out in each region how many new cases of this new disease there are. We change that. We make that more precise. What we do is, for each new infection, we tell everybody the network theoretic distance between them and that new infection at that moment of reporting personally. For each new infection, tell everyone their network theoretic distance, I'll call it network distance, personally, because everybody has a different network distance to the person who is just sick, and I will just say now. The point of the word now is only now. So later on, if that person who is sick continues walking around, no update. It is just that there's a new infection, everyone finds out now. It's analogous to saying how many new cases were there in the last 24 hours in your regions. It's much more precise now. Tells you how many new cases there were and how far away each case is from you. Now let's start to discuss why this is actually important. This is the game theory. Game theory and mathematics are about starting with something very simple and starting to think and then thinking about what that causes in terms of large-scale behavior. First of all, let's do some contrast. Right now, suppose that you found out that in your region, maybe in where I live, my region is my whole county. There are hundreds of thousands of people that live there. I think your regions might be similarly large. Suppose you found out that in your region with 100,000 people, there is exactly one new person who is sick in the last 24 hours. What would the average person think in that region? What would be the reaction if they found out that there is exactly one new person sick in the last 24 hours? Nothing. And the reason is because the typical person would say, there's one person sick. There are hundreds of thousands of people in my region. What's the chance that I'm going to run into this person? And this is where game theory comes in. System-wide, everyone would just go out. And the next day, you will have 2 new cases. And it still seems small out of hundreds of thousands. So everyone goes out because nobody knows any better. The next day, you have 4 new cases. And it just keeps growing until it's so much that either it becomes a lockdown or shutdown, or people just give up. Both of them are bad. What's the difference with this method? Suppose you found out that there's one new case. Well, actually, different people will find out different things about the new case. Some people will find out that the new case is 10 degrees of separation from them. Some people will find out that the new case is only 2 degrees of separation from them. Do you feel the difference between finding out that there is one new case in the entire region with hundreds of thousands of people versus finding that there's one new case that is 2 degrees of close, repeated physical contact from you? Meaning that that person spends lots of time with someone who spends lots of time with you. 2 degrees would be here, if you would be here. It's actually quite intense. Furthermore, it actually might be useful for you. To understand why this is useful, let me now talk about why this thing is actually potentially impactful, potentially highly impactful in protecting all of us from an even more deadly disease, and then we'll go back to talk about COVID as well. I want to discuss Ebola. Ebola is a disease for which, if you get it, your chance of dying is something like 50%. It can be even more in some outbreaks, but on the order of magnitude 50%. Ebola is terrible. And actually the problem with Ebola is that it's not just some science fiction. It's a real disease. In 2014, around 7 years ago, there was an outbreak that reached tens of thousands of people in Western Africa. It's very scary because the fatality rate is on the order of magnitude of 50%. And furthermore, there's a new mutant of that, a new variant, a new strain of Ebola every few years, maybe every 2 years or so. So it's something to be worried about. And unfortunately, these things keep mutating and the world gets more and more connected. So we should actually care that we have just found out that we cannot control even COVID. And if we had something that killed half the people, which maybe in a few decades will run around the world, we're really not ready. We need to do something. Oh, let's think about what this tool would do. First of all, if you do a simple thought experiment, imagine that there is a strain of Ebola which is running around, and imagine it has already struck in Puerto Rico, and 10 people are sick, they have gotten 10 more people sick, and half of those people who got sick died. And everyone knows that. How many people in Puerto Rico would want to download an app where it's voluntary to download the app, but if you have it, it will tell you that, oh, somebody just got struck with this disease that kills half the people it strikes, and that person was how many degrees of contact from you? Do you think this is something that people would somehow want to have? They're watching on the news that half the people are dying. Yes, it's actually very interesting. That's the power of game theory. The value of this tool is that it actually is to your benefit to have it. It doesn't matter what your politics are, what your beliefs are. If you have something that's actually killing half the people, of course you want to have it, because it's your radar to let you know about threats. But wait a second. Weren't there some apps that were made and even pushed by Apple and Google on billions of people worldwide? There were some other apps. How does this compare? It's very useful, very, very important to contrast what I've just described here against all of the other apps in existence that were pushed on billions of people. Actually, they are fundamentally different. Let me explain this way. All of the other apps that were pushed on people during this pandemic had the functionality where they will tell you after you have already been around somebody who's sick. And the purpose of the app is to tell you, since you already have been around someone who is sick, you should do a lot of things to make sure you don't get anybody else sick from you. What's the difference? The app, this tool that I've just described is one that tells you, every new case tells you how far away it is from you in network theoretic distance. What's the difference functionally for the person? It's huge. It provides no defense. The difference is the original one, the thing that everybody was trying to do before, is designed only to tell you after you have already been around somebody who's sick. So unfortunately, from the point of view of many people in the world decided they just didn't want to download apps that will only tell them after they have already been around someone who's sick. Whereas what we have invented is something where you can find out before, by having something like a radar that tells you there's a danger coming. Actually, we've done informal surveys, and one reason I'm so interested in talking to University of Puerto Rico community is because this is actually active research. This is not only a tool that can help, it's also that we are collaborating with scientists to understand the impact of this on all kinds of different populations in the world. And for example, if any of you are connected to other researchers at University of Puerto Rico who do social science research or public health research or mathematics or computer science, and you'd like to collaborate, we would love to be also doing these informal surveys formally and in your community as well, so that we can understand how many different areas in the world would respond to something like this. But based on what we have learned in many other parts of the world through informal surveys, this is actually a compelling tool. That if there is something that is killing half the people, people want to have it. Please define the way you use the term game theory. Yes, game theory is this area of, I don't know what to call it. It overlaps with mathematics, it overlaps with behavioral science. By game theory, what I'm referring to is that you have some way that the world works. Those are the rules. And game theory is where you start to analyze how will a person react given a situation and given the rules, but also given that they are working inside this system with other people as well. So game theory is something where you think about a lot of usually independent agents, which are trying to, well, actually not only independent, but lots of agents, which are people trying to make decisions to make the best decision to help them advance what they want to advance. And that's just why I'm using all of these incentives. I'm talking about all these incentives. The key concept in game theory that this is getting towards is the concept of Nash equilibrium or prisoner's dilemma. These are concepts where you might have a better societal outcome if everybody just did the right thing. But unfortunately, because individually their incentive structure is to not do the right thing, you don't get to that nice equilibrium point of everyone doing the right thing. So that's actually why I mentioned the word game theory. And in some sense, when we were trying to control pandemics before, we were hoping to just have everybody do the right thing, and then we'll be able to stop the virus. For example, the easiest way to stop this virus is that every single person in the entire world just stays home and doesn't go outside for the next 2 months. Then it's over. But unfortunately, that's so unrealistic because individually there will be so much room for people to do the wrong thing. Okay, but so that's what I'm referring to there. But now back to this concept here. It's that yes, I would love to be doing work with your scientists and your researchers as well. So if anyone wants to reach out to me afterwards, I'd love to be able to document that these claims are actually true, right? Because right now all I'm talking about is the theoretical foundations for this approach, although they're based on what seems to be common sense. But the bottom line is, if you go back to this concept of a situation where people actually want to survive, then this is a tool that people would actually want to use. Second question, suppose that you have this tool. Suppose that people are using this tool. How would the average person react if they saw that there is disease striking, and it is striking closer and closer to them personally? How would the average person react? What I mean is, imagine that a person saw that this 50% fatal disease is striking. It used to strike 10 people away, but then it's striking 8 people away, 7, 5 people away, 4 people away, 3 people away. What would an average person do in that environment if they had this lethal disease, which is striking people who spend time with people who spend time with people who spend time with them? What would they do? Some people would get a test. Some people would reduce contacts. Some people would take precautions. But generally speaking, you're seeing that people would start to do things that are designed to isolate. But the interesting thing here is nobody forced them to. Right? The principle here is there's a very different incentive structure. Back to talking about the game theory, there's a different incentive structure when you find out that the disease is striking closer and closer to you, but not yet striking somebody that you already spent time with, right? So actually what's going on here is this is a dynamic which can cause those people who are farther from the sick person, but not that far, to start taking caution. And the interesting thing is this actually gives you a way to start to separate these people. The reason I talk about game theory is because the way that we have been trying to control disease for centuries has been to go and find the people who are sick and the people around them, which are all the potentially dangerous people, and try to control them against their will. This approach empowers everyone else to try to stay away from getting too close to someone who's sick, but it does it anonymously and while we protect privacy. The main point is you don't actually need to know who is the sick person. All you need to know is your network theoretic distance. Actually, the way that this is even designed, I can go here. The way this is designed, it actually shows you how the disease is progressing towards you. So the way to read this chart is that the height of a bar is how many people are sick, and this degree of connection is telling you how far away in network theoretic distance that new infection has just struck. And if you saw, it was changing over time. I'll play it again. So the way this works is that it changes over time. The date is changing. And as the date changes, you can see, the disease striking people maybe closer and closer. This is actually a pretty scary picture. But the point is that this doesn't need to tell you who it is. Just knowing that there's a danger coming closer is a way for you to be able to protect yourself. And so that's why I say what we've come up with here is something that could actually have major implications on how you are able to protect societies, free societies, against infections in the future. Because this system is actually powered by selfish incentives in terms of people wanting to be part of the system, and also people wanting to take certain actions to protect themselves when the disease is striking closer and closer. And effectively, it creates a separation. But the separation is all of these people's own ideas. And the beauty of it is, if you think about what this would do to the transmission of a virus, in theory, what this would do, in theory, is that wherever you have the sickness, you're not really, this method doesn't control the sick person or the people around them. Use other things for that. But this empowers all of the other people outside to go and take some action to protect themselves, which actually still causes these two groups of people to be more separated, which actually contributes, potentially, to slowing the spread of a virus. I've been talking about this to scientific groups for the last year, all over the world, all different kinds of scientists. And surprisingly, this angle of putting forward this kind of a value proposition and then relying on game theory and behavior to power a feedback loop is actually new. I'm very happy to talk to you about this because I also saw that through the efforts of people, including, well, actually spearheaded by Arturo, there actually have been people in the University of Puerto Rico community who have been interested in this system and even interested in using this system to try to stay safer, even amidst COVID. I can tell you a little bit about what we have seen with, say, something like this in a university context. Actually, I was just talking last night with students from Caltech. That's because the Caltech student government, these are students, the Caltech students, their leaders, the student leaders contacted me because they were interested in finding ways to try to help avoid getting sick. The way it works over at Caltech is that people get tested actually twice a week. No matter whether they have symptoms or not, everyone gets tested twice a week. And so over there, actually people don't want to get sick because if you actually get sick, whether you die or not, you get inconvenienced for 10 days because that test is going to catch and find out that you were sick. In that environment, it's very interesting. It was not a situation where the university leadership, the administration didn't come down and tell the students, you have to use this. The students came to us saying, we want ways to not get quarantined, if that makes sense. So the point is, this is actually a tool that you can use if you want to not get sick. How? What you do is, if you actually are using this tool at scale, then if you happen to see that disease has struck somebody who spends a lot of time with somebody who spends a lot of time with you, well then that's a good time to go and take some action to protect yourself. And that's where it gets also into the question of how do you protect yourself? Well, here is the deep fact, which is that unfortunately not all masks are equal. It's not that deep actually, this is a shallow fact, but not all masks are equal. And a lot of masks, such as those cloth masks, they actually don't really do a great job of protecting you against other people. They help to protect other people against you if you happen to be sick. That's why we wear masks. In Carnegie Mellon, we wear masks everywhere because everybody is protecting everyone else against them. However, if you actually have something which is in your vicinity, in your social vicinity, it's in your interest to actually wear a better mask, like an N95 mask. And then when you wear a better mask, now that not only helps you protect other people, but it is also effective at protecting you against virus coming into you. And so a very practical thing you can do is, if you have a system like this set up, which gives this warning telling how far away disease has struck, well then, you can actually combine that together with better masks so that whenever something strikes too close, you actually can protect yourself. Okay, so let's talk about how this actual implementation is, because people are curious. I was actually talking about the outline of the structure and the architecture because that's actually the main innovation. Nobody had thought about this architecture before. In terms of how it's built, we actually just, use engineering. So that was also fun. That was what we did for the last year. So we built an app. It runs on iPhones, it runs on Androids. The way it works is that this particular app uses Bluetooth to automatically talk to other nearby phones which also have the app installed. every few minutes it uses Bluetooth to ping and say, is there anybody else around here who has this app installed? And based on the strength of the Bluetooth signal that it receives back from the other guy, it estimates how far away the other person is. Now, this is designed to be anonymous. So the way it works is that when you install the app, it does not take any information. No email address, no name, no phone number. It also does not record the GPS because the GPS latitude and longitude would sometimes identify who you are based on where your GPS is at 3 a.m. So the way that our system works is that these phones which have the app installed are automatically building the network. We see this happening before our eyes. So for example, I can just pull mine up. I'm at Carnegie Mellon University right now. Unfortunately, I'm too far from the camera, so it doesn't really focus on this. But I'm just holding up what my app looks like right now. I can actually see these are not sick people. This is just telling me that there are 258 other people which are connected to me through this network. And the heights of these bars, you can't see because the resolution is too low, but the heights of these bars are telling me that I spend time around 7 people. Those 7 people spend time around 19 people. Those 19 people spend time around 95 people, and so on. So this network was constructed just by me having this phone in my pocket, walking around, and other phones talking to this phone. That's how the network is constructed. It's automatic. And importantly, the only information we have about people is this is a smartphone, and it has a user ID, which has been generated as a random number at the moment that the app was installed. So that's how we map the network. There's actually deeper questions of how to make a better network. We're working on that right now. We're thinking of other ways to even try to deduce which connections in the network are more relevant. What about security and battery drain? Oh yes, great, happy to talk about that. For security, the way that this is designed is it takes no personal information in the first place. So there is no personal data to leak. In terms of I also talk to privacy researchers. I'm a graph theorist. I'm a network theorist myself. I will say that in theory, if you had all of this information about this anonymous person was around that anonymous person, you might be able to start to guess what cities people live in. If you looked at the entire map of all these people using this system, you might be able to guess that these people live in these cities. From a security perspective, if you have this entire network of anonymous user ID talking to other anonymous user ID, then yes, in theory, you can start to deduce some things like city. You might even be able to deduce things like who is in a very high density area, like in a university dormitory. And you'd be able to start to deduce these sorts of things. What we do is we try to make sure that we don't have anything that would help that deduction. And yes, we do have this centralized information store. But the way we see this is that our centralized information store has far less centralized information than Apple itself and Facebook and all of the people that you're using your phones to do things with. To answer your question, but I will also say the bottom line about the security and the privacy is they are things we take seriously. I'm always happy to talk to people if you're a security researcher as well. We always want to make things as good as they can be. But the key innovation here is the architecture, because if you actually think about it, yes, a lot of people are concerned about security, but what they really have is they have a security or privacy budget, which is what they're willing to spend for something that will help them. And although there were all these apps earlier, and everybody raised a lot of noise about security and privacy, our analysis is that actually what people were complaining about wasn't the security and the privacy. It was that the app doesn't do anything to help me, so I'm not willing to give up even any security and privacy. Because all of those apps, if you install them or don't install them, they don't directly help you. They only give you a chance that you might have to be quarantined. And so then people said, well, then I don't like all of these security and privacy things. But on the other hand, the thing that made us have the confidence to know that this is something where actually security and privacy are important, but not the number one criteria people look at, is the Apple AirTag. I don't know if you've heard of this, but there's this AirTag that you can buy, which is so I see there's another question. I'll hit that too. So the AirTag is this device that you can buy, you can put around in your backpack, and you'll never lose your backpack again. And everyone hailed that, not everyone, a lot of people hailed that as a great thing. Even CNN said it's a must-have for college students. You only have to pay Apple $20-some, and then you'll get a device where the only principle of the device is if you lost your backpack, it talks to other people's iPhones, uses the GPS of the other people's iPhones, and tells you where your backpack is. That's actually tracking far more. And everyone thought it was a great idea. That's because it delivered something that helped you. And so that's why for us, the key innovation was the architectural innovation, which is in the future, within 30 years, when there is a pandemic that kills half the people it touches, this is what you want. Because at that point, the people's decisions will be, do I care about losing some tiny amount of privacy, or not tiny, I can't quantify that, but losing some amount of privacy, and is it worth it in exchange for being able to see this 50% lethal disease coming my way? Actually, that decision is most likely going to go in the direction of wanting to save yourself, save your life. There's another question here. There were two questions. Let me answer this one real quick. Battery life. Yeah, let's find out. I'm curious. So, battery life, here we go. Battery life. So, I mean, this is just my phone right now. So I just have my phone, and on my phone, I can pull this up. And what you can see, actually, I don't know if you can see. It's probably too small. But I held up my phone, and I can look at how much it's using. And so, for example, I'll just tell you, on my phone, it happens to be using approximately the same amount of battery life as what's called exposure notifications. I actually have both of them on the screen. Exposure notifications is actually the standard system Apple made. Apple and Google made a system that was supposed to be reasonable on battery life. Mine said 9%, exposure notifications was 8%. That's what it was today. So we're on the same order of magnitude, not even order of magnitude. We're basically the same as that. And these are designed so that it actually doesn't take much battery. And in fact, as we keep improving the system, it will use less and less battery because unlike the exposure notifications, we actually don't need to just track those short interactions. What we're most interested in are who spends lots of time together with who else. So in theory, we can actually reduce our scan frequency even. So this alternative architecture actually opens up a totally different battery drain amount, which is actually potentially much better. Now let's continue with the next question. How is the illness recorded in the method? That's very important. So the way this works is that because it's anonymous, we will not have any automatic entry of illness. So the way this works is that if you happen to get sick, there's a button you can press to report that you got sick. That's not going to do anything. So now, unfortunately, you can't rely on people just being nice people to report. By the way, there are issues of how do you know the person's actually sick? Well, when we're actually working with an area, what happens is that the local health group, whether it happens to be the university or the school or the county or the region, whenever there's someone who's sick, they give the sick person a passcode. Then that passcode can be entered to indicate that you're sick. The value of this is that you get rid of the false positives. Not get rid of, but you reduce the false positives by a lot. However, there's the false negative problem, which actually people making these apps did not address. They actually just said that most people or half the people will be nice people. We disagree. From the get-go, we said that we think only 10% of people are nice people who will say that they're sick. Everyone else glossed it over. What we do is we have two buttons. Our app is the only one in the world where we thought that we should add two buttons. One button says, I am sick. The other button says, I was around somebody who was sick. And the second one can also be verified because in most universities, there's actually normal contact tracing going on. This is actually another one of our key innovations, which is that we can have a button where if you're contact traced to be around someone who's positive, then you also get a passcode. You can enter that one to verify that you were around somebody who was sick. Actually, these passcodes, for example, at one of the places that we are implemented, we have it built into their IT infrastructure. So whenever their health center finds that someone is sick or contact traces someone to have been around someone who's sick, automatically these codes are sent, right? So these are automatically sent and it's done. So at that point, we have these two things. Why is this relevant? The reason this is relevant is because actually, in our paradigm, where we're telling you how far away the sickness is from you, in terms of people contacts, it's actually also useful to find out that there's a person who was around somebody who was sick because of what is called the triangle inequality in mathematics. In mathematics, the concept is if you found out that 2 degrees of physical contact away from you, let me just draw that out. I will just draw dots now instead of stick figures. But if you found out, so suppose this is you. I don't want such a thick pen. Suppose this is you. If you found out that 2 degrees of contact away, there is somebody who was a contact traced contact of sick person Well, what does that mean? That's actually very useful. That's telling you that there's a sick person within one person of that. Who's the sick person? I don't know. Maybe here, maybe here, maybe here. But the point is that you're able to know that the sickness has struck within distance 3 of you. And from the point of view of our app is supposed to help alert you when we find out that there is some danger which is relevant to you. This thing tells you the danger distance and it's off by plus or minus 1 in terms of what we could do if the person who was actually sick had reported. The reason why this is important is because even if the sick person themselves never presses the button, the typical sick person, suppose this was the sick person, the typical sick person in today's society might be around 10 other people. And suddenly, all of those 10 people, of course, this is a network. The network can have all kinds of different ways of interconnecting. But what I'm trying to say is that all of those people all have a chance in order to report that they were around the sick person. And what that does is technically, it amplifies our input signal by a factor of 5 to 10. It's an order of magnitude if there were 5 to 10 people who were contact traced to have been around that sick person. So suddenly, even though only a small fraction of people will actually press their button, what this does is it makes it so that those small fraction of people who press their button already give signal that lets everybody else see that there is some danger that has just struck somewhere nearby. The analogy here is if you think about how, let's say, a warship is using radar to detect enemy aircraft, there are more and more ways to make aircraft stealthy. And now, stealthy doesn't mean that the aircraft is undetectable. It just means that many parts of the aircraft don't reflect the radar. But sometimes when the aircraft has a certain angle, there might be something reflecting off the wingtip, the wing of like the tip of the wing of the aircraft. Well, at that point, it's okay. It's still useful. If your radar is showing you that there's this thing moving towards you, something is moving towards you at twice the speed of sound, and if it's the wingtip of the enemy bomber, still useful because there's a bomber attached to that wingtip. That's the same principle here. It's that yes, there's a sick person, but even if the sick person doesn't voluntarily report, one of the other people around them, if they report that they were around a sick person, it's still useful in letting you know that disease is coming your way. So that was actually another one of the key ideas in this work. So at that point, we now have a way of getting signal into the system where it maintains the anonymity and it actually resolves the problem that was glossed over by people who made all of the other apps because they couldn't solve that problem. But we solved that problem by switching to network theoretic distance. Why does the app use the microphone? Actually, it doesn't anymore, really. The microphone is actually an optional thing. I'll tell you what we used the microphone for in the past. Okay, so the bottom line is, if you don't want the app to use the microphone, just don't accept the permission. The whole app works. All right. The reason why we had the microphone thing is because actually Bluetooth is very hard to calibrate. If you just use that you got some Bluetooth signal power from the other phone, the issue is that every phone transmits at a different signal power. So how in the world do you know how far away it is? Actually, I did these experiments in this room. I'm in a laboratory right now. And in this room, I was just measuring the transmission powers of all these different phones. They vary quite wildly. And you could imagine that's the case because different phones have different shapes, different sizes. The antennas are located in different places. So actually, just because you got a Bluetooth signal from the other phone with some strength doesn't directly translate into how far away that is. Also, if you happen to have a background in signals, if you work in Bluetooth, you also know that it's extremely noisy. And even the estimates are wildly off sometimes. Well, early on in the whole pandemic, we were making an app that was a standard contact tracing app. And our approach was to help you do contact tracing apps better. So we used the microphone to implement an ultrasonic-based system. So earlier on, what we were focusing on was making an app for which we would actually accurately measure the distance between two phones. That was quite fun. That was actually that was some serious mathematics and engineering. But as we did that, we used the microphone because you would make an ultrasonic ping, sort of like sonar. And then you go, no, actually not like sonar. Sonar is based on reflections. But we'd make a ping and we'd go and measure how long it took time-wise for the sonic ping to get from one phone to the other using the microphone. And we would therefore, at that time, have the most accurate app for contact tracing. But then we realized that that doesn't even work anyway from human incentives. So the microphone piece is that we had gone through all the effort to write the code so that two phones could accurately measure their distance between each other. And then what did we do? Well, the reason why it's optional now is because anyone who opts in, we're not listening to anything you make. We don't care about that. What we do is we're using the small percent of people who opted in to turning on ultrasonic scanning to mass calibrate all of the devices Bluetooth. What do I mean? Well, the issue is that there are 10,000 different Android device models. It's too labor intensive, too much work to go and put all of these, to buy one of every Android device and measure the transmission powers and everything. Actually, the way Google and Apple calibrated their system, they actually asked manufacturers and asked people to go and put devices on tripods at different angles, at 1 meter apart, and do measurements. You know how we did it? We used math, and we used algorithms and computer science, because what we had is we had an automatic system for some pairs of devices. We already have both of them opting into the ultrasound, and so we were able to have this data collected from the whole field of all these devices in the field. Some fraction of them opted into helping us calibrate. We used the fact that in the field the ultrasonic pings were going on at the same time as the Bluetooth pings, and it's a math problem then. It's a noisy inequalities math problem to go and say, can we work out the right parameters for transmission powers and actually also receipt attenuations? There's two variables per device model. We estimated these device model parameters using the fact that some people opted in to give us an actual accurate measurement of the distance between devices. So that was like that was fun. But yeah, you don't have to turn it on. If you don't like it, just don't turn it on. The core principle of this is just a new way to avoid disease. And to close this whole talk, what I'll say is actually using this app is most valuable if the university also gets interested. Please repeat the math details, algorithms to implement the app. What exactly do you mean by repeat the algorithms? I guess I never told you the algorithm that we use. It's just an algorithm to calculate how far away from you is each positive person. What is the math behind it? Okay, well, let me close this first because I want to mention a few things first because there might be some people who have to leave to something else. What I'll say is that the real value of this will be if the University of Puerto Rico administration also gets interested. And then suddenly you guys can issue those passcodes. We'll work with you. We'll make it so that when your IT system for the normal health center is telling people they're positive or that they're contact traced, we can make all that stuff automatic. And so if any of you happen to have scientific backgrounds and want to work together on this and can help to approach the University of Puerto Rico leadership, we'd be very happy to help you because this is actually a scientific endeavor where if we can prove that this has efficacy, this is actually going to affect how pandemics are controlled worldwide because we're building that knowledge base to be able to handle that lethal pandemic of the future. I'm now going to switch over to questions because I see that there are these specific questions here. What is the math behind? Well, we used a few kinds of math here. One piece of math was what we just saw here. Oh, what is the name of the app? Well, the app is called Novid. No COVID, N-O-V-I-D. But again, the biggest value of this is if we can get the administration to be interested in this alternative approach. Right, so now math behind. There's a couple of different places that math is important. One part that is relevant for is what I just shared with you about this, what I call the triangle inequality, of the fact that if there is a person who is a contact of a sick person, then the sick person is within that distance plus one of them. That's an extremely important point because this suddenly makes it so that our app works even if many people don't do what they're supposed to do. That's a very important principle. Another part of the math that comes into this is just the general conception of how do you make analysis and deductions starting from one new approach, one new system, or one new change of rules. I mean, what we do in mathematics is we make all kinds of deductions based on a new definition. And so this is what happened here, make the deductions of what would that do for human behavior across an entire system. There's also more math in us knowing that this system will work even before everybody installs the app. That's also important. That's related to network theory. Again, that's the area of math I work in. It turns out that the network structure of human interaction networks is fundamentally different from totally random networks. And it's easy for anyone to understand why. Because a totally random network, if you were going to be connected to 10 people, the chance that you're connected to someone in Siberia or Saudi Arabia or Moscow or San Juan or Miami or Madison, Wisconsin, they're all the same. All the same probability in a random network. Now, actually, in this random network, in that random network, it's almost the structure of your network is what's called a tree. Where you are around you is like a tree. So it's very susceptible to not many people having the app installed. But in the real human networks, if you think about what's going on at your university, if you have two people, and if those two people have one common physical contact, it usually is true that there are actually many common physical contacts. This is called a small world effect. Sometimes these are called small world networks. But this is a characteristic of human networks. So that's actually something that gives us the confidence to know that this is going to connect up people and give them useful information even before you have everybody using the app. Because now if you have a lot of redundancy between two people, even if some of them aren't using the app, you still can get information that, oh, maybe this one's using the app. Okay, well then these two people really are degree 2 contacts, distance 2 apart. Nash equilibrium, yes there is. Actually the Nash equilibrium for this is very interesting. It's actually that everyone has, so I should be clear. There are two Nash equilibria. The first Nash equilibrium is that nobody has the app installed, right? So this is a great question. What are the Nash equilibria? So a Nash equilibrium means that it's people doing these behaviors and nobody has any incentive to change their own behavior, okay? So the first Nash equilibrium is nobody has the app installed. And if nobody has the app installed, you have no incentive to install the app because there will be no network. But the funny thing is we have a second one. Everybody installed. This is extremely powerful. Because the standard contact tracing app only has the first Nash equilibrium. We have two. The reason we have two is because if everybody has the app installed except you, if you install it, just think about it. You get the power of information coming from everyone else who has it installed, and that information is designed to help you avoid getting infected. Yeah, it helps you. Whereas if you think about the standard contact tracing app, if everybody else has it installed and you install it, that doesn't change your chance of getting infected. That just makes it so that if you get infected, you can protect other people. And since everyone else has it installed, they're already protecting you against them. So this is extremely important. We have two Nash equilibria. And the other beauty of this is that we can move out of the first one very rapidly. That uses more network theory. It's actually because whenever you happen to have a network where the average person is around 2 or 3 other people who are using the system, then you get very large interconnected connected components, which are sub-networks of people who spend time around people who spend time around people, and it keeps going. And the point here is that in order to make the average person have 2 or 3 other contacts on average, you don't need to have everybody install the app. The average person might be around 20 or 30 other people. That might be a 10% level. So we're then able to move over. Yes, and how do we get to the Nash equilibrium 2? That's actually where these kinds of talks come in. Right, so what I'm saying is that once you get over the point of connecting people, then there's a clear value proposition, like just what I did. I just showed you my Carnegie Mellon network. Anyone that I'm around at Carnegie Mellon, they don't need to wait for the network to come anymore. You're out of one. My point is that we're already out of one, out of equilibrium 1. We're on our way to equilibrium 2, because I can just show, look, we have 250 people already on this who are connected to me. So it's actually already got a network built. If you install it, you're connected to me. You gain all 250 people's relaying of information to you right now. So how do you move from equilibrium 1 to 2? It's through letting people know what the app actually does. Because the problem, what we have found is the problem, is most of the people don't even know that our system is fundamentally different from contact tracing apps. Because Google and Apple spent so much effort and other people spent so much money advertising the concept that was wrong. They were advertising the concept to say, you should get an app so that after you already were around someone sick, you can be a nice person and not get anyone else sick. And they try to push that into everyone's minds. So much so that when people hear about this, they say, oh, I already made a decision. I don't want that app. They don't understand that this is different. So that's where talks like this are useful. Whenever we are rolling this out at a university, if we have the support of the university leadership, the way we do this is that we actually organize sessions in every residential community. We give talks in engineering groups. We make it so that everybody needs to hear and understand that there's a fundamentally different approach to fighting pandemics that they are now part of. And this is not actually just some standard thing. This is actually something that could unveil new technology that will save many people in the world in the future. Basic stats about the app: number of users, accuracy, user satisfaction, etc. Well, I'll say I'm not going to oversell. This is something where most people don't know it exists. So basic stats about the app: how many users? We probably right now only have something around 1,000 active people who are using, maybe 2,000 active users for the app. If you look at the website, you'll see that there are 100,000 plus people who have downloaded it at some point to take a look. So I'll say that puts us into the realm of bigger than most academic projects, and with the critical mass that could take off to actually derive some useful information about this and help people. But this is not at the scale of, say, those Google Apple things where they spent millions of dollars to convince people to download. We didn't have millions of dollars. Accuracy seems okay. I mean, it seems reasonable. The networks that I see on my own app look reasonable. Remember, accuracy here is not that we care so much about really being and saying this is really a 6 foot or 7 foot. This tool is designed to help you. And when it's designed to help you, it's okay if the error bars are a bit more generous, because you'd rather see more danger than less. User satisfaction seems okay. I mean, that also seems okay. The reviews on the App Store and the reviews on Google Play Store seem quite positive. I should say that people who are using this and understand what it does are also excited about that too. But I think the bottom line is the biggest hurdle is people don't know what this is. Created by mathematicians. Yeah, perhaps. I mean, whatever helps. But I think the main thing that we're trying to do is we're trying to help people understand that it's not even just an app. It's a totally new paradigm for disease control. And that's actually why I'm working on it. If you look at my history and you look me up, you'll see that I'm not like some app maker, right? Like, I'm actually a researcher. And the things that I and our team are interested in doing go far beyond COVID. The reason why we're pushing this so hard in COVID is because the only way to convince scientific community of the power of a new paradigm is with data. It's like all these questions you're asking. And you can't get the data unless you're actually being used by some people. If there were no COVID pandemic, we'd never get any data. Because if there's no COVID pandemic, no one's going to install some app to tell them about the flu. They're not worried about the flu. But the point is, if you can use the fact that there is a COVID pandemic to learn from the science and collaborate with your scientists at UPR, not just scientists, your professors, researchers, and scientists at UPR, we could actually develop the body of knowledge that it takes to convince the entire public health community that this is a very powerful method that should be put into place when that 50% lethal contagious disease strikes in the world. And if we do that, that's a reasonable contribution to society. Any other questions? We're over time. I think we're over time. I was told it was 1 hour. So I understand that people have to go. I'll just say the biggest impact here would be if we could convince the leadership that this is actually very worth taking seriously. And it's more than just about COVID now. We already have a hypothesis, not we, I think a lot of people have a hypothesis that COVID is here to stay. It's going to stay, it's going to keep mutating, and who knows, if there's a mutant that ends up breaking through all the vaccines and actually killing people, you really need to have solutions. And the time to make solutions is not when that already happens. So if we can find a way to work with your administrators and work together on the science, we could potentially put this thing out, learn something, protect everyone. And if there's some mutant later, you guys will be in great shape. You won't need to roll out again. Oh, there's a hand raised. Oh, I also see there's a... Yes, please, please. Hector.
The typo is breakup. Have you contact Apple or Google with this application?
I have actually talked to the person in charge of this at Apple, the person in charge of the Apple system. The bottom line is that they are actually not that powerful. So again, the person I talked to is the person in charge of the system at Apple. But they are not in charge of Apple. Do you know who's in charge of Apple? The shareholders. Apple is not a company whose purpose is to make the world a better place. Their objective is to make more money for the shareholders. That is their job. That is the purpose of an American corporation. The same is true for Google. And so unfortunately, it looks like Apple and Google are controlling all of the innovation. Well, actually, they're not controlling all the innovation. They're controlling the distribution for that particular type of system. And this was all started as a PR effort in the first place. So it's ironic. Yes, they know who we are. They're not going to put this in now because the rest of the world doesn't know what it is. And they might be scared because what is this new thing? Actually, people already were scared that Apple and Google were doing something at all. And so it's ironic that what we are doing is we're not working with Apple and Google because they're doing their own thing. But we are going to establish that this is actually how you fight disease. And guess what? After we succeed and we convince everyone that this is what you do, Apple and Google, because they know exactly what we're doing, they'll put it in iOS 17 or 18 or something. And it will be hailed as a great new feature for iOS. And what I'll say is great. Then I'm happy. Then we succeeded. My definition of success and why I'm working on this, my definition of success would be that within the next 2 to 5 years, the entire scientific community is in consensus that this method makes sense and should be used for future pandemics. Actually, I think even a 5th grader would agree. This does not require fancy knowledge. It actually just makes sense. And so if we manage to do that, Google and Apple's PR department will say, well, now there's no risk in us putting it in iOS 17, so we will. And so the bottom line is Apple and Google know very much what we are doing. They're just not able to put it in. And what we are doing is we're trying to prove to the whole world that this is a no-brainer and you should put it in. And hopefully in the future, it will be in.
Thank you. I wish you luck and very nice explanation.
Yeah, thank you. Thank you. Oh, I also see that there's a comment. Thank you for making the comment about the colloquium and the UPR enforces Novid. I want to make one small change to that statement. I don't want anyone to feel like Novid got enforced. Enforced is the wrong word because this aligns with incentives. All we need is that the UPR leadership says this makes sense and then authorizes us to talk to people to just explain why this makes sense and why you actually want it. Then you don't have to enforce it. It's just like what I described with the Caltech undergraduate community. If people understand what this can do to you and also understand that it doesn't cost you anything and doesn't collect anything, doesn't collect any of your personal information, then if you don't want to get sick, this is the app for you. So enforcement, I think, is actually counterproductive. What we need is just that it's official. What research projects are running based on this? This is fun. I don't know if you're a researcher or not, but I'm happy to tell you what we're doing. So we have multiple different collaborations going on right now. So I originally wrote the theoretical paper that says, here's why in theory this will help. That one is the first thing that came out. That's on the archive. Then after that, I ended up talking to somebody who works in an intersection of behavioral science and public health. And so we have something else that's not necessarily research. That's another theoretical work that we're working on writing. That's another theoretical work which discusses the theory and also from the public health perspective how those would interplay theoretically. We also have another research project which is ongoing, which is based on simulations. We are working together with actually a leading group. They're at Oxford. And what we're doing is we are simulating out what would happen in a pandemic situation if this was deployed and if people did something about it. That's ongoing. We did that. I was working with one of my students on that, and also our collaborators. We have another ongoing research project with they are in human-computer interaction, which is user experience design, but from the computer science perspective. And what we are doing there is we're conducting surveys, formal surveys, to go and understand whether or not human behavior does indeed align in this way. There's a new collaboration which is springing up now with a political scientist. Political science is also relevant if you want to deploy something on grand scale. And that one we're looking potentially to do even more precise surveys that will dig into this aspect of, is this actually something that works from a human incentive perspective? This is what already exists. We expect that more could come out of this. And I spend all of my time now talking to people who work on other areas of math and science, actually now primarily science, in order to try to motivate more people to do research on this. And my expectation, by the way, is as more people do research on this, I expect that the results will be quite good, because in theory this should work out. And what we could do with this is we could potentially open an entire area, an entire direction of research, which is what happens when you combine game theory together with engineering, or this sort of systems engineering, together with public health. Could be very interesting. Oh, Spanish is already in the interface. I think. It should be. I think that if your phone is in Spanish, the entire app is in Spanish. Yes. And I'm very proud to say that Spanish, I think this is true. When we released the iPhone app, we actually had it in Spanish as the very first. Well, I know this is true. Spanish was the first translation. We've had it in Spanish for a while. A while meaning since something like May of 2020. So we take this very seriously. And to me, your community is actually extremely important. So I would love to work with you. Great. Any other questions?
Dr. Lowe, I want to thank you personally for the talk. I hope we get to Nash equilibrium number 2. I hope we get support from the administration. I'm convinced that your ideas and the app will do wonders for this pandemic and for the future. And well, we'll see what comes of this talk and whether we can move forward with this.
Wonderful. Great pleasure talking to you. Okay. Have a great day.
Thank you. Thank you to everyone that attended the talk.
Yep. Bye-bye.